have any on the chat window, so I'll try and visit once in a while. So shall I start?
Yes, go ahead, please.
Okay, so so I'm going to talk about essentially cloud workloads and why they're really relevant to computer architecture. Why people who work on computer architecture should understand what cloud workloads are. I'm not going to be able to cover everything here, but I just want to give you a sample of what uh, you know things are. So what I want to cover is first I'm going to give you an overview of what's really cloud computing. I mean, it's a fairly clouded topic. What's really cloud computing? Some small definition we will start with and then get into it. Then I'm going to look at what are different cloud computing models. I mean, you would have heard of the term, EAS, PaaS, SaaS, PaaS, PaaS. I don't know how many asses are there, but what are really these cloud computing models? And little bit demystify that. Then I'm going to go over to see how did programming models evolve with the cloud. Start what programming models are we all comfortable with, and then to see based on these cloud computing models, how did the programming model itself evolve. And because of the evolution of these programming models and of these software stack out there, what are the implications on the architecture? That's essentially going to be what this talk is about. I don't think I can cover everything because this is a fairly vast area. I'll try and give some feel to it. Please feel free to stop me and ask questions if you are in doubt about something. Okay, so the first question is, why do we really need to understand, why is it important for us to look at cloud? As you can see here, the main thing is that we've always designed computer architectures, have always designed them based on mainly high performance computing applications. We've taken all of these high performance applications like molecular dynamics or we have taken things like databases, Oracle's data center applications like Oracle, or web servers, what web servers are running. And we've tried to model these and use these as representativeness. Kanishka in the morning talked about representative workloads. So we tried to model some of the workloads based on what would generally be running on most of these on-premise. Like to distinguish between on-premise and cloud, between the cloud and on-premise servers, and say that we design something that can be used by our hardware, which can be used by customers running such applications. But you can see with advent of the cloud over the last 10 years or so, it's like exponentially growing, and most people are running their software on the cloud now. You can see just growing exponentially, more and more of this spending is happening on the cloud. People are spending more hardware. Cloud service providers as like Amazon and Google and all of them are spending a lot of money on equipping the cloud. Hence, it's important to understand what kind of workloads run on the cloud, and hence, what are we going to be designing our systems for? Okay, that's in essence. Some of these are already a little bit more mature, and some of these we are learning as we go along, and we are trying to respond as architects. We need to start responding to what the needs are. Okay, so this is one definition. By no means this is from NIST. It says cloud computing is a model for enabling ubiquitous, convenient, on-demand network access. Okay, that's a key part, to a shared pool of configurable computing resources that can be rapidly provisioned and released with minimal management effort or service provider interaction. Just quite a mouthful. So if I were to understand the lines, the ones which are underlined out there, those are the important ones. It's ubiquitous, which means if to understand this, maybe it's easier if we take something else, like the difference between owning a car and using Ola or Uber, right? Where you want the idea between owning a car and buying a car is what we're saying is you want to enable ubiquitous means that it is always available. It's convenient when you want, you can on demand meaning when you want to a computer, you can get some computing resources. It's where does these computing resources come from? They come from a shared pool and you access them over the network. They come from a shared pool of configurable computing resources. It's not like you have just one type of resource. You can choose the type of resource that you want, and it can be rapidly provisioned. It's not like you have to wait days on end to get a machine. Today, if you want to buy a machine, the amount of process that you will have to go through to get a machine is takes months, and before it will get, there be a tender, it will be released, then by the time something else will happen, you will get your machine. That takes a few months to buy a machine. Whereas in the cloud, when you want a machine, it can get rapidly provisioned, which means that you want a machine now, yeah, you can get a machine now. You can get some computing resources now, you can get those computing resources when you need them. This is very much similar to the way you want Ola or Uber. You don't need to have a car, you don't need to own a car. Ola and Uber cars are there everywhere. Hopefully they're convenient. I mean, they don't cancel, but it's on demand. When you need them, you can take a car, you can use it, and you can give it back. And because it gets picked from a shared pool of cars. And it's rapidly provisioned. If you want it now, you get it now. It's not like you want a car now and it tells you I'll give it to you at 5 p.m. in the evening, right? So that's not this, and you don't need, it's minimal management effort, which also means that you don't need a manager to approve that you will be allocated a car. So that's not required. So that's the idea of a car being used in the cloud. So this is the whole notion of the cloud, where the resources are not with you, the resources are somewhere else. So to understand a little more of how things developed, let's first take a look at the simplest cloud model there was, which was called the EAS model, which is infrastructure as a service. So what happens here, typically what you would do when you needed to run some software was you would go and buy hardware for it. And today what happens is you don't really buy the hardware. The cloud provider buys hardware. What the cloud provider tells you is the cloud provider allocates some piece of the hardware for you to run. He allocates what is called a virtual machine. A virtual machine, we'll see a little later what constitutes a virtual machine, but it essentially virtualizes the hardware resources. For us, what are hardware resources? CPU, memory, IO devices, right? That's what would be hardware devices. Typical examples of cloud service providers who would do this are examples like the basic AWS when it started, and Rackspace. Okay, these are vendors which provide. By no means these are exhaustive. I just give you some examples. So this is, you have the hardware, and when you want, you ask for a VM, and you say I want a virtual machine that has 4 CPUs, that has 10 GB of RAM or 8 GB of RAM, and I want it to run Ubuntu 20.04. Okay, it's up to you then most of the time. After that, once the OS is installed and given to you, it's up to you to write whatever software you want to install on top of that. It's up to you to do that. If you want to install Oracle on it, so be it. If you want to install a web server on that software, so be it. So it's up to the user to determine what software they want to run on it. The resources are virtual and provided to the user. Okay, so this is the basic infrastructure as a service. Next, what happened was it evolved into the cloud service provider saying that, hey, I'm not just going to give you a VM. So for example, if you are writing a web-based application, you know that for most web-based application, you need a web server. So most of the vendors ended up, if you go and get a VM, you ended up installing a web server on it. or you installed a database on it. So what the platform of the service provider say that we'll give you a VM, but we'll give you a VM already with something installed on it. This will save you some time. So we will give you a VM with Apache JBoss installed on it, which is a application server, or we'll give you something with a web server Nginx installed on it, or a database like MySQL previously installed on it. You can use this for developing your applications quickly. So if you are an application developer, you don't need to, and you want to deploy your application, you don't really need to worry about how, you don't really need to worry about installing a web server, installing a database server. All of this headache is taken away from you. The PaaS provider will provide instances with all of this, and you can focus on what you do best, which is writing your applications. That's how PaaS is, and Azure essentially started off as a PaaS. Microsoft Azure was a PaaS provider. The next one, and this is very common, and you're all familiar with this, for example, Gmail, which is, if I were to look at where the software itself is available on the cloud provider, gives you the software also along with it. So if you as an end user only want to do email, okay, then use email. Why are you really worried about how many servers are being used, how much hardware is being used? You don't bother about all of those. From an end user's perspective, when you try to look at the thing, the end user is only interested in running these applications, or a CRM applications like Salesforce. They only want to track customers. Take, for example, somebody like Airtel, or one of those banks which keeps calling you to say that, hey, do you want a new credit card? How are they tracking you? It's using this software called CRM. And this CRM application runs on a SaaS-based application, because the Airtel or the bank or whoever is only interested in tracking customers. They are not really interested in, are you having a VM, or are you running this on a machine? They're not interested in all of this. They just want to make sure that as many customers they want to call and maintain in their database, you will allow them to maintain. Okay, and whatever their flows are, you will customize them. So it's a little bit on saying that it's the hardware is completely abstracted away from the application user. For now, just for your this whole discussion that we are doing, the Teams on Teams is also a SaaS application. You don't know where it's running. You don't know. You only interact with it. Okay, sorry, the last one that should read FaaS as function as a service and not SaaS. Function as a service is essentially, as you decide, say you want to run a small, you want to run something which you're doing only one small function. Your application is only, like, for example, you want to you're trying to use Google and you're trying to use it in the voice. So you give it the voice and ask it to translate to text. So that's a small function which takes a voice and converts it into text. So think of it as a function. So, and you only want to execute this function. You're not interested in a large of things. So you want this function does, given an input, generates an output. The infrastructure, as a cloud provider, we will provide you all of the infrastructure that you need. You just write a function, give it to us, give us what you tell us. Whenever the input is there, we will automatically run the input on that function and give you the result. We will decide how many instances of this function will run. You pay only for the time your application runs, right? So it's a great way of saving money, because you don't need to really, once you have a VM, every time for all the time the VM is up and all the storage that you do, you need to pay for all that time. But even whether customers are using it or not, if nobody is coming to your machine also, no problem, you have to pay for that time. Whereas in function as a service, you pay only for the time your function executes. So it's economically very nice for the customers to use this. So if I want to look at a quick overview of all the cloud service models, well, at the very bottom, you have the bare metal, or the bare metal is the one where you got it on premise, you got hardware, and you're actually working with hardware. And then you have EAS, PaaS, SaaS, FaaS as different models of this. The difference being, as you start from, there's more and more flexibility as you go down. Fast, there's least flexibility, and as you go down to bare metal, you have the greatest flexibility, which means you can decide which OS to install, you can decide which libraries to install, you can decide how to connect it. It's all up to you. Whereas with fast, you don't know what OS is running on. You just write a function, you just give it in one language, and the application runs it for you. That's all. The infrastructure runs it for you. You don't even know which OS it is running on, which machine it is running on. Nothing you know about it. Okay? So the greater flexibility when you want, you go in for something like bare metal, and the lesser flexibility that you want, you go in for something like fast or less cost also. The second thing that you need to observe is that as we go from bare metal to fast, there's more automation. Automatically scaling happens, which means more and more instances of functions can be run, or more instances of database servers could be run automatically when you go towards fast, which means there is a software middleware layer which is running, monitoring your system, and actively performing some tasks there. So as architects, when we look at it, typically when you look at bare metal, it's just an application which runs on hardware. As you go from bare metal up to fast, you have more and more software layers that come in between that start to influence performance, and that the hardware needs to be aware of and make adjustments so that it can cater better to the customers. We can logically stop at this point. If there are any questions, I will take them.
In this particular right hand side arrow, where there is software written, so the amount of software also increases.
Pardon? Sorry. Yeah.
In this arrow, the right hand side which points upwards, here software is written, so as the amount of software also increases.
Yes, the software infrastructure software also increases. It's not just your program, and I will give you, as we go along, we'll get an idea of what those are.
Okay, thank you.
Okay. Let's stop and take a look at how the programming model has evolved. This is something that all of us are quite comfortable with. We take our laptops, or we take our any server, something which is what we call bare metal, and we write these monolithic programs, right? We write these programs. Let's assume that we are writing a small application which is doing some kind of a e-shop kind of thing. So you will have, let's take something called Flipkart or something like that, or Amazon, where you're having you have two functions here. One is you search for an item, and then you have something where you add to cart. Right? You have two such functions. So you'll kind of write code for it, different C files, C++, Java, whatever, compile them together, create this program, and then run this program on the hardware. Right? So it's very clear, it's just this one piece of software which you're running, which is going to control the performance of what's running on your hardware. Of course, you would also run, if this is using a database, then you would also run a database. But how do IT people typically deploy programs is that they would run database programs on different machines and application programs on different machines. They will never mix the two of them on the same machine. Well, the simple reason is that they don't want database performance to be impacted by the other one, or for some matter, if some problem occurs, they can just simply replace this. And each one of these machines is very carefully tuned for the application that it is running on. So you can pretty much have different kinds of slightly different hardware which is running on each one of these. You may want more storage on the database machines, whereas you may want more processing power on the application servers and the web servers, which get the request. So, but the model is this. The model is still that you have a monolithic program. Everything is in one big box, and you run this on a database. Now, how does this change when we go to something like infrastructure as a service? Structure of the service, what we do is we don't run it on a bare metal machine, but we could pretty much run the same thing on a single virtual machine. Take the existing program which you were running on a physical machine, run the same thing on a virtual machine using a virtual disk. You could be running both on pretty much a single VM, or for just to mimic the way it was done in the other way, you could run it on two different VMs. Key being that this would be a virtual disk, and you would access the database actually over the network. So this is a virtual disk, and the DB write gets translated to a network access automatically over two VMs. Okay, I'm not going to talk about challenges of how to access from one VM. How do you access the other network? That's a completely different area by itself. But just for now, assume that you can magically write from one VM to another VM. So we are still in the land of where we are writing these monolithic programs. Now, the question is, what really is a VM? He said that it virtualizes CPU, but how does it really virtualize CPU? That's a quick this, which I'm going to take now and some time and give you a feel for what really is a VM. This is our notion of a machine, which we have in the bare metal without the virtualization. You have a machine. The machine consists of some CPU, it consists of memory, disk, network. These are all IO devices, and you run an OS on top of this. Right? You run an operating system on top of it, and we run an application on top of it, on top of the OS, which means that every time you want to do some IO, you would pretty much make a request to the OS, and the OS will make a request to, let's say, the disk or the network to do the IO. If you want to allocate more memory, you again go to the OS, which controls, how the memory is allocated. Right? So this is how things work without virtualization in a bare metal environment. Now, let's look at how it would look in a virtualized environment. In a virtualized environment, what really happens is that the hardware, just focus on the bottom part of it. On top of the hardware directly, we don't run the OS, but what runs is what is called the virtual machine monitor, or more commonly known as the hypervisor. Okay, so this is the one which controls all of the hardware, the machine. And what the VMM does is it gives in a field, it kind of partitions this and says, I will create a virtual machine which has a virtual CPU, some virtual memory, some virtual disk, and virtual network address. I will give this field to the layer above me, and that layer is an OS. So there's an OS which runs on top of this virtual machine. So this virtual machine is very, very similar to this machine here. So in the sense that this could be a 16 core machine, whereas the CPU, virtual CPU here is 2 cores. You can say create for me a virtual machine with 2 cores, 4 GB RAM and 100 GB of connect 100 GB hard disk to it with some networking this. So the virtual machine monitor kind of carves out or says that, okay, here is your virtual machine with 2 CPUs in it, 2 cores in it. The OS then would see 2 cores, right? The OS would be able to run data things on 2 cores. Now, if you want to try this out yourself, I don't know how many of you are familiar, but you can download a very simple virtual machine like VirtualBox. I think many of you would have done that. You can download VirtualBox and run it on your laptops, and you can create virtual machines there. What we don't know though, this OS here doesn't know what is the real configuration of the machine down below. It only understands the VM which is given to it here. So it's isolated. The application runs on top of this OS. Similarly, on this side, what you have is you have another VM. So this could be 2 CPUs, 2 cores, and you could have another 2 cores on this side, or maybe even 4 cores. And we have out here, we have a 16 core machine. So this could be 2 GB and this could be 4 GB. Pardon my handwriting, but yes. So you could break up your VMs to have different configurations out here. You could be running 2 different OSs here. You could be running Ubuntu 18 or Ubuntu 20. That's what we wanted originally. And you could be running Red Hat here, RHEL, Red Hat here, or you could be running Windows here. You could have 2 different OSs, different applications that run on top of these OSs. Right? Any questions as of now?
The hypervisor requires one more OS, right? I mean,
not really. Okay, so there are 2 models which we find. There's one model which is called a type 1 or a bare metal hypervisor, which runs directly on hardware. Your example for that is things like ESX, VMware ESX or something, which runs directly on hardware. There's a second type of virtual machine which is called a virtual box, which runs on top of the OS, which is called a hosted hypervisor. Yes. Sorry, could you repeat your question, please? Type down your question if that's an Gautam. You could type down your question if the hope it was clear. So there are 2 types of hypervisors. There's the type 1 hypervisor which runs directly, and this is what is used in most production environments. You could also run the model where you have the bare metal machine, you run an OS on top of it, and you run a hypervisor on top of the OS. Your VirtualBox is an example of this. This is okay when you have, although it will have performance issues, but this is fine because you will run, you can try it out on your machines. For that purpose, where you want to try out, this is a good way to try. So now the question is, how really does this whole thing work? How does this application? So if you see here, this application runs on an OS which needs to execute on this virtual CPU. But you know now that you have a pipeline and you have your front end and a back end, and your processor goes on fetching instructions and executing them. How does it know that it has to really work? So one way out is that this is how it works. So what does it do? Let's assume that you have this instruction here, move R1 from contents of location 1000. That's what the instruction you're executing in this application. So this virtual CPU has to read this instruction. It has to interpret it and it has to execute it. Okay, so the VMM, which is running here, this virtual CPU, is responsible for executing this instruction. So one way to really do this is it needs to simulate every instruction. It needs to know that if I have every instruction, I will decode it and I will run it. Which means for executing one instruction, you are actually doing a lot of work to just run one instruction. Now, practically that is not very easy to do, or not very comfortable to do. So what people were doing is that if you understand that the ISA of this, the ISA of this and the ISA of the machine is the same. If this is the same, then you could pretty much run this instruction directly on the machine. Right? So the application could be run directly on the hardware, and it would run at the speed of the machine, not at the speed of the VMM, or not the speed of getting simulated. Do you foresee any problem with running the application directly on the machine? Do you foresee any problem of running directly the instructions directly on the hardware? Anybody?
I think scheduling is a very big problem.
What do you mean by scheduling?
As in basically providing a priority and switching the priority on the fly.
Okay, so for all practical purposes, this is a process. This is another process. So so question is, who does scheduling? Does the VMM do scheduling, or the guest OS does scheduling? The next question is, does the guest OS even know? So this is called a guest OS. The OS which runs on the VM is called a guest OS. Does the guest OS even know that it is running on a VM? For most part, most guest OSs are, we use this technique called transparent virtualization, where the guest OS is not even aware that it's running on top of a VM. It's unmodified. You can download the version of Ubuntu that is available on the net, and you can download it, install the same thing on the machine, install the same thing on the VM. So the guest OS is not really aware that it is running on a VMM. So the problem really is that most instructions, there is no issue, you can run it directly on the machine. But there are certain instructions which may not work well. Like, for example, syscall instruction. You're trying to do a system call instruction. The system call instruction cannot run directly on, on the hardware. Why is that? The reason is that these are all called sensitive instructions. They require much higher privileges to run. You know that OS executes at a much higher privilege level. So typically speaking, the OS will run here. So to understand this, on the x86 architecture, we have something called privilege rings. This is the highest privilege. This is the lowest privilege. Under normal circumstances, what will happen is the OS will execute at ring 0 and the application will execute at ring 3, sorry. Whenever the application makes a system call, it will jump directly to the OS which is running on ring 0, and all of the executions, all of the stuff which runs in ring 0, or privilege instructions which can run in ring 0 will work properly. There's no issue about it. It can run directly with hardware, can execute it. The challenge happens when you start having the VMM. The VMM is the only one now. So we must remember one thing. Hardware must be controlled only by one person. So the allocations must be controlled by one person. And in this case, the VMM must be running on ring 0. So where to make space for the guest OS? So what we do is we make space for the guest OS on ring 1. We run at a much lower privilege level than ring 1. But here you cannot really control the hardware. You can only control the hardware when you are in ring 0. So the guest OS, which ideally ought to be as an OS, it ought to be running on ring 0, but in the case of VM, it runs on ring 1. Now the problem is this: when I wanted to do something in the guest OS, I needed to do the system call. I need to switch into the guest OS, or but really I can't do that because I'm switching into the VMM. So what the VMM needs to do is it needs to understand where the request is coming from and route it to the correct guest OS. That's one. Second one is that the guest OS itself may execute a privilege instruction. What happens in this case? So typically when a guest, so I would say run the instruction on the hardware. If it's a privilege run instruction which is running in a privilege level much lower than what it needs, like for example, it needs to be in ring 0 when it executes the privilege instruction, but the guest OS is in ring 1. So what happens? It should generate a trap. Okay, it generates a trap, which means then once the trap is generated, the particular instruction, it says, oh, this particular instruction is not supposed to be run in ring 1. I will run it for you. I will emulate it for you. I will do whatever that's supposed to do. I will emulate it for you and give you back. You can continue executing the guest OS. So the VM runs on, which is VM guest OS, which is running on ring 1, is emulated by the hypervisor. The hypervisor takes over the tasks of whichever ones require higher privilege levels and executes it on behalf of the guest OS. Okay, is this concept clear to you?
Yes.
If so, then the issue then becomes that if it's running there, the one issue could be is that we never really designed our architecture to work for working with virtual machines. We never really assumed that there will be something like a VMM, which will, take care of all the guest OSs. Second thing was not all guest instructions, not all privilege instructions actually generated trap. On the x86, there are a few instructions, there are about 17 instructions, one of which is the popf, the flag register, pop the top of the stack into the flag register. This particular instruction does not generate a trap when it is run at a lower privilege level. So if it doesn't generate a trap, there is no way it can be emulated. Right? And it all happens really because we are trying to use the innovation in software came, but the architecture was not ready for it. So now, how can we kind of solve this problem from an architectural standpoint? Well, the answer is pretty simple. What we do is we make the hardware aware of the fact that there is a VMM which is going to sit, and there's going to be also a guest OS. So we create two modes of operation for the processor. The processor can run in root mode, which is this. This is the root mode. In the root mode, the VMM runs in the root mode. So the VMM runs in ring 0 of the root mode. So all the rings are available in both the root mode and the non-root mode. The guest runs in the non-root mode. So this now starts to look exactly like how it would look on bare metal, where the guest application runs on ring 3 and the guest OS runs on ring 0. But really, this is non-root mode, which means that we know that we are inside a VM. We would have this one is the root mode, where the VMM is the only one which runs in ring 0. In addition, we have explicit instructions which will allow you to go from here to here. Here you can exit. So you launch a VM and you can exit from the VM to the root mode. Okay, both AMDV and Intel VTX are examples of how this is implemented. The next problem happens is you learned earlier in this about page tables. So the challenge is now that the guest OS also has page tables, right? So any page translations that is being done should be done by the guest OS, right? But the virtualization challenge is you could have multiple guest OS, and physical memory is really owned by the VMM. So what generally happens is there is a two-step mapping where the mapping happens from the guest, you can call it the GVA, the guest virtual address. From the guest virtual address, it has to be mapped to first the guest physical address. Okay, this is the notion the guest has of physical address. When you allocated a 2 GB RAM memory for a VM, you know that your memory is from the guest VM, or the guest OS knows that it has physical memory from 0 to 2 GB, right? But in reality, that memory could be spread anywhere inside the actual physical memory of the physical machine. So another translation has to happen from the guest physical address to what is called the host physical address. HPA. So two steps of translations have to happen, which means twice you need to do table lookup. So in software, they solved this problem in terms of using something called shadow page tables. Shadow page tables. We will not go into the details of this. This was done in software. Which means you have two page tables. Essentially, you have one guest virtual address to guest physical address page table, and you have a guest physical address to a host physical address page table. Now, this is solved by what's doing is that we created a single page table such that part of the page table is updated by the guest OS and part of the page table is updated by the hypervisor in hardware. So what you can do is that you have two page tables, one for this and one for this. What we can do in hardware is we can make sure that when there is a page to be loaded, you need to do a page table walk, which means that you need to look up the given the virtual address, you need to look up the physical address. Now in hardware, once you look up this physical address here, this will be used to index into this table. And from here you get the actual physical address, and this will be used for doing your actual lookup from memory. Now, in the earlier case, when you have to do it completely in software, you have to do a hack to enter in the physical address here using the shadow page table concept. But when your hardware was started capable of doing this, you could do this thing called nested or extended page table, where this part of the page table is owned by the guest OS, and this part of the page table is owned by VMM. And there are two of them. They're pointers to both of them. And then when you have want to load a page, you will do this translation. Part of the translation automatically The hardware will look up the second table, look up the translation, and then load it from there. Okay, so this is how architects had to respond and add features inside the hardware, inside the processor to take care of virtual machines for both CPU as well as for memory. Now there's also much more work to be done in terms of I/O and I/O, how to handle I/O in terms of virtualization. So there's a lot of development that happened in order to support running on virtual machines. Right? So this kind of concludes a little bit, very short summary of what hardware had to respond to in order to handle something like virtualization support. Are there any questions with this? There's some question which says, where does ABIs fit in this block diagram? Prithvi, could you kind of highlight ABIs? What really do you mean by ABIs? I'm not sure. Any question regarding this?
Where do Docker and
Hold on.
Yeah.
You're wanting to know why does Docker come into the picture?
Yes.
Hold on for a minute and I will kind of address your question. I'm just coming to that next.
Okay, thank you.
Any other question? Okay, then let's move on to looking at how programming model further had to evolve. Now, one of the challenges of running things on the VM is the fact that the VM has, as you know, to start a VM, you need to start not just the VM, you need to start an OS inside the VM. The operating system has to boot up inside the VM. So spinning up a VM is actually a time-consuming job. Though there are a lot of benefits, it's still a time-consuming job spinning up a VM. So some of the technologies that people started developing in software was to do something called a container. A container can be thought of as some sort of a what do you call it? Lightweight VM. It's a sandbox environment. Essentially, it's a process. We took advantage of the fact that processes also give some amount of isolation. So if we could add more isolation to the process concept, then we could make, instead of really starting a complete new VM, most of the time we are very happy not really requiring a new OS, but we just want to make sure that I can somehow protect my process from other processes. So this was the notion of what was called container, which started coming in. So the technology that was developed was container, and containers allowed you to use virtualization, pushed virtualization from hardware down from virtualization to the OS by providing what are called separate namespaces. Okay. So using that, the next technique that we started seeing was this evolution of programming model, was we started to see most of these applications started to move to the microservice model. So in the microservice model, what happens is that the two functions that you start to do, one looking for an inventory and the other one cart management, start to now move to different containers. You implement it as part of a container. This gives you isolation for this application. You have another application here which is just handling the cart part of it. That moves to a different container. You could run these two containers. They're really lightweight. They're two processes. The advantage is that if you start to see more and more people starting to search for items, you can create more instances of the search for item container. You can have 10 instances of the search for item container, and you can have one instance of the add to cart container because there's more activity here. You don't have to duplicate the entire program per se. The second advantage that it gave from a software development perspective was you could have completely different teams working on these two. You could design these two using different languages. You could be using completely different databases to do these two. All that you had to do was you had to make sure that this interface was well defined. And people tended to use REST as a mechanism to make a call from here to here. REST stands for representation state transfer, or a remote procedure call, Google RPC or one of those, to make a call from this process to this process. And these two processes could pretty much run on different machines, or they could be running on the same machine also. Next change that you started to see was this. You were always seeing this, that this is accessed over the network. The database is accessed over the network. The third change is that rather than an organization or a machine, we were planning to run a single database. We started to see this scenario where you're going to be using completely different databases for doing different things. For example, a shopping cart is not very well represented in SQL kind of a database, whereas inventory may be easily represented in an SQL database. This could be using something like a key value store just to store this. I'll come to this. Right. So challenge now, lots of access over the network. Different kinds of databases suddenly are going to be available for you to run and use simultaneously. And you're going to do all of this REST RPC, which requires transferring from this format to the network format and back. So what architectural challenges do we have? Containers are like isolated processes, but hardware is not aware of them. And often every container has its own software stack. We are starting to see far more variety in the software stack with containers. Some of the observations that initial studies tend to show is that you are going to be running, whereas you'll be running very few number of VMs on a single physical machines. With containers, you're going to be seeing large number of containers that are going to be running, maybe thousands of containers which might run on a single machine compared to VMs. Second is that this observation in performance where you start to see that an operation which used to take X amount of time now takes more instructions per request. A request, so how a request comes in, you process the request in a kind of a monolithic way if it takes X amount of time, with which is called the path length, because it's the number of instructions that are executed per request. We started to see 3x number of instructions required to process the same request, simply because you have to do networking, you have to do synchronization. The software stack started occupying more time than just the application itself. The application plus the software stack started to see 3x the number of instructions that were required to process a certain request. It was still beneficial because you have the benefit of scaling out, which you started to see. But from a hardware point, what do we see? We see that the diversity in workloads is huge. This is one study done in 2019, where in Facebook, where they looked at the fact that there were these 3 different types of microservices which they were running, 3 or 4. There's the web part of it. There's some caching, which is in terms of a database server, some caching which is done, and there's this ad recommendation for ads and all of this. All of them were running as microservices. All of these 3 would have completely different behaviors on how they use the architecture. So we know this, right? The front end is an iCache, fetch and decode. Kanishka kind of went over this today, and the back end of the architecture is the execute and data cache and dispatch, and how the UOPS are dispatched. What they observed was these applications showed only about 20 to 40% of utilization of the CPU. Right? They were not efficient in utilizing the CPU. The CPU was not being utilized. All the hardware was not being utilized. Why they were not being utilized? An analysis of this kind of showed that a large amount of time which is there, the pipeline was stalled in the front end in applications like the web. The web application had a very large code footprint, right? And this was not allowing the web was having a lot number because of that it would have cache misses, and it also had a large number of branch mispredicts, which caused the utilization to go down and a lot of stalls going down because the backend was not busy. Backend didn't have work enough to do. The front end was not able to get for the web application, it was not able to get enough instructions in time. Second thing that we saw was that they saw that it very frequently context switches. The microservice does a little small thing and then immediately context switches. It doesn't have much work to do. Right? Because of this, it's not able to also build up enough history in terms of branch predicts. But that's not all of the applications behave that way. Right? An application like ads resulted in backend stalls because of data cache limitations. Okay? So ads had a different behavior, web had a different behavior, and cache had a different behavior. So we are having to design a single architecture which has completely different requirements. One where the front end is stalled, the other one where the back end is stalled. So how do you go about designing architectures where you have different kind of behavior on different kinds of applications? One possible thought to how to handle this is to have certain knobs in hardware and let the application modify it as it deems fit. For example, we could give a knob, that there are knobs today which allows the L3 cache to be dynamically partitioned. You could give certain codes certain lines in that L3 cache and certain codes certain other areas of the L3 cache. You could partition the L3 cache across different cores which will be running different applications. So you could do this soft kind of dynamically, you could have the software be able to take advantage of different partition the resources dynamically. This is one solution which we could do. Another solutions which starting to see is that as we increase the number of cores, we have this opportunity to co-locate some of the microservices on the same machine itself. Typically, microservices would run, service A would run on machine 1, service B would run on machine 2. But if you are having 64, 128 cores, or even 256 cores like what AMD has, why not co-locate these onto the same core, onto different cores of the same machine, right? Would that help you get better performance? So that's what that's one paper which Shreyash kind of explored last year. We're also starting to see other things where networking between these services starts to dominate. Okay? And you're translating data from one format which is in memory to another format which is on the wire. So can we use accelerators to do these data transformation? That's where another piece. So much of the work that is being happening now is more saying that what are the various things that we can try and do. But some of these have not made their way into real architectures. Or more time is actually being spent in about 80% of the time. One of the analysis which says that 80% of the time is actually spent in the orchestration layer, like something like Kubernetes, which is running. We have multiple layers like that, Kubernetes, Docker. So much of the time you're not spending doing work in the application, but you're spending time with this orchestration layers which are there. So how can we optimize that? Can we use accelerators for doing things like compression? Or can we use accelerators for doing things like encryption if encryption is required? So this is an area where people are starting to look at and say, maybe these are potential for how architecture needs to respond to handling things like microservices. What we also see is that we have diversity of databases. Earlier, we only had this one SQL database. This new notion of what is called polyglot persistence is that you have multiple different types of databases. Key value stores are like hash tables. They're essentially gigantic hash tables where you have a key and you have a value, and you want to insert data into the database. You only have to do something like give the key and add the value. Clearly, such kind of architectures don't have very high locality of reference because they're using key and values to do. Redis is one example of a key value store. A second type of database which is there is a columnar database. A document database is similar to a key value store, except the fact that the value is in some structure like a JSON or XML. So then it becomes important for document databases. Can we do JSON parsing faster? Columnar databases are mainly used for, normally databases are stored row after row on disk. Columnar databases aren't like that. They are stored columns. They're broken up into some related columns together, and they're stored column after columns. And these are excellent when you're trying to do analytics, because when you're doing analytics, you tend to access just a few columns, but you access all the rows of the same column. Unlike transactional applications where you're accessing one row or few rows at a time, here you will access all the rows, but only a few columns. So it makes more sense to save your database on disk in a way in which it's easily read. So how do we kind of handle columnar databases? And finally, you have graph databases where you are actually storing the structure of the graph inside the database, where you have vertices and you have edges. Each one of these has very different in terms of access patterns, and a single application could potentially use more than one such database. If so, as we start to see this, if so, how do we start building, and especially when it comes to analytics, people start to write queries which are extremely large. They're not writing these small queries with one or two predicates, but they're writing key queries with hundreds of predicates. If you're writing such queries with hundreds of predicates, do we have the hardware? Do we have the capability to process these 100 predicates quickly? So what are the challenges there? We don't know. So these are all areas which will probably have to be explored, and they're all coming from the database angle. Okay, so we'll move to the last part of it, which is FAS. So in FAS, what happens is that you write a function, it's basically a container, where you say, okay, I want to recognize a face in an image, and it gets deployed. It gets deployed as a container, and you will then pass it a stream of images. As and when an image comes up, you pass it through a load balancer, you pass it to the container. As the load goes up on the system, it scales by adding multiple instances of this container. Right? So the load balancer then is responsible for pushing requests to multiple containers. Right? So this is how it works. Function as a service works. Now the challenge is the following. The challenge is that your container must be kept ready when you're deployed it. It must be kept ready for execution. When the image comes in, somehow if your container is sleeping, it must be run. Second aspect of the container is that a quick start time. The second aspect of the container is that most of the time in FAS, the work that is done is pretty small. The amount of code that is executed is very, very small. So because of this, what happens is there's one work which has just started last year. We saw a paper on this. Is that under low load conditions, the system actually spends more time starting and pausing containers rather than actually doing work. Okay. Next thing we started to see is one of the analysis showed that branch mispredicts. If the functions are really small, then the language runtime which is there, like say Python, Python will have to start running a function. Language runtime dominates over the function. Okay, and there's not enough time to train the the branch predictors with the functions behavior. What really happens is the language runtime at that point tends to dominate. Uh, Work also is kind of demonstrated that these are really small functions. They're not really sensitive to very large LLC or last level cache sizes. It's with smaller LLC can more or less manage. It's still work in progress. There's a lot of challenges in executing function as a service and seeing where the challenges are. So with that, I kind of come to an end. We haven't covered some of the other cloud workloads simply because it's don't have the time. Gone already quite fast over the whole concept. Things like ML and how Google responded with the TPU, or others also responded to this. I think Amazon responded with some inference engines. So ML is a completely different area where, because of power reasons for speech processing, the Intel came, Google came up with this solution using systolic arrays and not using the traditional von Neumann model for architectures. The next thing that we also not covered in this particular talk, I just want to leave you with a feel for, is the security needs in the cloud. In the cloud, typically your application of one customer and another customer could be pretty much running on the same physical hardware. This is called multi-tenancy. So two tenants who are sharing a single physical hardware. From a performance point of view, it causes problem because one may interfere with the other, which is called the noisy neighbor problem. But from a security viewpoint, you don't want the tenant may be running some financial application, and he may be really worried that the hypervisor can see what my data is, and what if he breaks into this, he might be able to get access to the hardware. So people requested for more security, and I think the vendors have responded with encrypting the pages as they are written to the memory, to DRAM. Okay, so what I wanted to leave with you is that hardware and software both have to coexist. They have to closely collaborate. In changes in one tend to lead to changes in the other, and that's what I hope this diagram will kind of represent. And cloud is one big change that has happened in the last few years, and that's starting to play a big difference in the way we are architecting our hardware. I stop at this. We have a few minutes, about 5-6 minutes, for me to handle a few questions. Feel free to either type or unmute yourself and ask a question.
In that containers, you were showing that web application cache and ads were handled in, as in it was having these kind of issues. How did you manage to get this data? I mean,
this is there in this paper. You can read this paper.
okay.
I will put link, maybe the I will share the link. It's not a problem. You can, the paper is titled this paper is titled Soft Skew.
Okay.
I'll put it down here. Let me see if I. got hold of the paper. Let me see whether I can put it. You can get data from performance counters.
As in, how did we get to know that this is from web application or this is from ads or cache? I mean, that is because
that's a challenge. You can essentially you can do it by two things. You can pin it to a particular core and then get information from that.
Okay.
So this is an exciting area. I mean, all the hardware vendors, and you can see Amazon's AWS starting to build its own hardware. Intel is doing its, AMD is doing in this area a lot of work. Very exciting area for a very exciting time for computer scientists. There were some of you also asked for some papers on doing performance analysis systematically last time. I have added those papers to the Performance Lab channel. Links to those papers, you can read it from there. Any other question? Okay. I think Madhura, there's no other question, then I think we're all getting hungry, I guess.
Yeah, I don't know. I guess.
Last day, Friday evening.
Yeah, thank you. Anyway, thanks for
Welcome.
bringing in some nice points. I hope you can make it for the session in the evening.
Yeah, I'll be there and then you can.
Yeah. All right. Thank you, and look forward to more interactions as we move forward.
I hope you guys enjoyed it.
Thank you, sir.